And so now what we need to do is talk about what position and velocity and displacement and acceleration are in terms of vectors. So we know how to calculate vector components. And how to do vector calculations once we have them in components. So now we just have to define position, velocity, and acceleration as vectors. And I'm going to go through the definitions sort of the same way I did in 1D, but I'm not going to take as long. The definitions are pretty similar to what they were in 1D. It's just now things can move all over the place. So position. So like, if you think of the position vector as like the location of this train again. This time the train isn't confined to a track, so it has wings. And once you choose a coordinate system, so let's say that we're going to keep track of where the train is based on its center of mass. Once you draw the coordinate system, so let's say this is our chosen coordinate system. And the position vector is the vector that goes from the origin of your coordinate system to the object. Okay, so that red vector with the head pointing to the train is the position vector. And if you think of this vector as having a length L and an angle theta, then the position vector is equal to L times the cosine of that angle theta, L times the sine of that angle theta. If the object is straight above or below or to the sides of the origin, so let's think of the coordinate system here. Okay, and let's think about what the position vectors would be for, let's say this, and this, and this, and this. Okay, so those are 4 possible locations for the object. Well, what would be the coordinates of that point? Let's say that distance is L. So let's say that distance is 6. Yeah, 6, 0. Okay, if that distance is 6, then the coordinates of that point are 6, 0, and so those are the components of the position vector. But if this is 6 away from the origin, so that would be, you have to, right, think about it as the coordinates of that point. If this distance is 6, you don't have to go anywhere along the x-axis. You just have to go 6 in the positive y direction. So this would be 0, 6. This one looks shorter. Let's say this is 3. So what would be the coordinates of that point? -3, 0. And then let's say this is also 3. So what would be the coordinates of that point? 0, -3. And so you can think of the position vector as being a vector from the origin to the object. Or you can also just think of the components of the position vector being the coordinates of the object in your coordinate system. It's the same thing. Any questions about that? So the next thing we have to define is velocity. Velocity measures how quickly the position is changing. And you would define it the same way that we did in 1D. You start out by defining the average velocity vector. So V average would be the position vector at the later instant minus the position vector at the earlier instant divided by the elapsed time. And then in order to define the instantaneous velocity, you would just pinch your 2 points, T1 and T2, closer and closer together and see where that velocity vector is heading. In 1D, the velocity vector was always in the direction the thing was moving, and that's still true in 2D and 3D also. So first, notice that the velocity vector always points in the direction that the object is moving. And so what that means is if you drew a path that the object's following, so let's say, for example, here's the XY coordinate system, and this is the path that the object follows. At any instant, the velocity is tangent to the path. So that's the velocity vector. And the velocity vector is tangent at any instant. And then there's one more thing about velocity. In one dimension, when an object was launched up into the air and it reached its highest point, what did we know about its velocity? It was 0. There's something like that in 2D, but now we can't assume that the whole velocity is 0. So when an object, let's say when a projectile reaches the highest point, the y component of the velocity is equal to 0, but not the x component. And it makes sense if you think about playing catch. You know, when you're playing catch, you probably sometimes catch the ball right at the highest point. If someone throws it basically horizontally, sometimes you catch it at the highest point. But you know that the ball doesn't have 0 velocity when you catch it. That would be like the ball is like stopping just as it hits your hand, like you wouldn't even feel it. You know, it maintains a horizontal velocity the whole time it's moving. I said that was the last one, but there is one more. So a lot of times we're going to have to figure out the velocity vector based on a speed and an angle. So for example, let's say that an object is launched at a speed of 20 meters per second at an angle of 10 degrees above the horizontal. That means that if you put your x-axis horizontal and your y-axis vertical, the velocity at the instant it's launched is going to make an angle of 10 degrees with the horizontal and have a magnitude of 20. And so to express that in components, you start at the positive x-axis, rotate 10 degrees to get to the vector, so theta is 10. And the velocity vector then is 20 times cosine of 10, 20 times sine of 10. And that's 19 point, I think that's 19.70. And 3.48, something like that. Any questions about any of those things with velocity? And then the last thing is acceleration. Acceleration measures. Question?
Yeah, real quick. So basically, when you found the velocity, those represent the x and y velocities, right?
Yes, that's right. Yep. So since 10 degrees is a really small angle, most of its speed is going horizontal and only a little bit is going up at that instant. What? Yeah. So this whole thing is units of meters per second. So the whole vector has the same unit always. And then acceleration measures how fast the velocity is changing. And there are two ways this can happen. One is speeding up or slowing down. I'm calling that one. And that was the only way that something could accelerate in one dimension. But, excuse me, now there's a new way that something can accelerate. In 2D, there's something going on that didn't exist in 1D. And that is the velocity is changing, even if the speed stays constant, the velocity is changing if the thing is turning. Okay. So, in 1D, you didn't have a choice of directions. All you could do was speed up, slow down until you stopped and were going the other way. But now there's this new thing that you can do this. And it takes acceleration to do that because the velocity is changing when that happens. So let me show you how that works, or give you sort of an intuitive thing that makes sense. So imagine being on this thing. It's this astronaut training thing that may or may not be a real thing, but they always show it in movies. So here's the astronaut in training. Nice hair. This thing's like zipping around in a fast circle. Follow what I'm trying to draw there. No? You know what I mean? Here, this will help. What if I... see what I mean? It's an astronaut. Now you know what I'm talking about? So this thing, it's like this training thing to help people learn to deal with really high G forces. And it spins you around, okay? And once it gets all the way up to speed, the speed is constant the whole way around. Like let's say the person's going 20 meters per second the whole way around, okay? So the person isn't accelerating based on the speed changing. There's a huge amount of acceleration. You know that feeling from like rides at Valley Fair or whatever. You can tell when you're being accelerated. On this thing, you have this strong feeling of being accelerated, and it's not from the speed changing. It's because at this instant, the person's velocity is this direction, and a little later, his velocity is this direction, and then this direction. It's just the changing directions that produces that big acceleration. So this is big accelerations without changing speed. Well, another example is like if you're driving your car on the highway and you don't notice that it says 40 miles per hour around this curve or whatever, and so you go into a curve at 50 that you shouldn't be or whatever. You know that feeling. That feeling is acceleration also, and it's not from speeding up a lot or slowing down a lot. It's just from changing directions quickly while you're going fast. So it's the same thing. That's acceleration, even though the speed isn't changing. And the most important thing that we'll deal with acceleration for constant acceleration problems has to do with free fall. In free fall problems, If you put the y-axis of your coordinate system up, which, once we start doing examples, you'll see that's what I always do. I think it's a good idea to just always do that. Then the acceleration vector is 0 horizontally, negative 9.81 meters per second squared for a y component. Okay, so now I'm going to give a set of steps for using the 2D constant acceleration equations. And the steps are going to look very much like the steps for 1D. They're just all going to be 2D versions of everything. And then we'll just spend some time doing example problems after that. So steps for using the two-dimensional constant acceleration equations. So in 1D, what was the first step? We're talking about like the VF equals VI plus ATF, those equations. What was the first thing I said to do? Yeah, you have to choose those four things. Time equals 0, time final, 0 position, and positive direction. In 2 dimensions, time doesn't change. It means the same thing it did in 1D. So you have to choose time equals 0 and time final just like you did before. So time equals 0, time final, those stay the same. Anybody have an idea what would be the two-dimensional version of choosing your 0 position? The origin of the coordinate system, yeah. So you have to choose where your origin is located, where your coordinate system's located. And then does anyone have an idea what would be the two-dimensional version of choosing the positive direction? That's right, just the orientation of the coordinate system axes. Usually for these, I don't think it's probably always true, but on free fall problems, I usually put the origin on the ground or the water or whatever the lowest point is in the problem, right beneath the object if time equals 0. And the coordinate system orientation for free fall problems, I'm always going to choose the y-axis up. For 1D problems, what was the next step? List out what we know and what we want. Do you remember how many variables there were that we had to account for in 1D? 6, I think. So there's time final, position initial, position final, velocity initial, velocity final, and acceleration. So 6. Now there's a whole bunch more because, like, for example, position initial has 2 components. Position final has 2 components. So there are 11 possible ones, and you have to account for each of them. Those are time final, position initial x and y, position final x and y, velocity initial x and y, velocity final x and y, and acceleration x and y. So it's a longer list of ones you have to go through, but it still works the same way. Just think through this list in the same order every time, and it'll be less likely that you accidentally miss thinking about one. And then step 3, just like in 1D, now we have to find an equation that, so we want to find an equation that has the variable you want, and all the other variables in the equation are known. And now there's not just 3 of these equations that are possibilities, there's 6 of them. And the 6 are, well, you can think of it as still the 3 main equations, but now we have one with all the x components and one with all the y components for each of them. I'm going to write them down here. So the first equation for 1D was VF equals VI plus ATF. So we have VF is equal to VI plus A times time final. I'll write that twice. And now one of the equations has all x components for the vectors, and the other one has all y components for the vectors. Remember, time isn't a vector, so that stays the same. And then the next equation said PF is equal to PI plus VI TF plus 1/2 A TF squared. Write that one twice. So the first one of these is the x components, and the second one is the y components. And then the fifth and sixth equations come from this one. 2 times A times the quantity PF minus PI is equal to VF squared minus VI squared. Write that twice. And so the first one is x components, and the second one is y components. And when I gave you these steps for 1D problems, I said there was one more that sometimes you have to do and sometimes you don't. Remember what this one was? Sometimes you have to use the quadratic to solve these equations, but that wasn't this last step. This last step was if it turned out that there wasn't an equation that worked, then sometimes you would have to find an intermediate variable that you could plug in. And I said that the intermediate variables were usually either acceleration or time final. That's going to happen more often in 2D than it did with 1D. But the good news is the intermediate variable is almost always the same. It's almost always time final. So if none work, find time final, TF, and then go back to step 2. Any questions about this? I think now what we need to do is just a bunch of example problems and a bunch of homework problems, and it'll sort of start to make sense. So let's say this baseball player here tried just like this. They have those stirrup sock things. Okay. So this baseball player winds up and throws this ball. So let's see that. Let's say he releases the ball from here. And let's say the ball is released at an angle of 25 degrees. The speed of, let's say, 40 meters per second. So ball's released 40 meters per second at 25 degrees above the horizontal. How far will the ball travel horizontally before it hits the ground? Okay, so I said that, so there's the ground. Unless there's some reason to do something different, I always put the origin of the coordinate system on the ground right beneath where the object is at time equals 0. Oh, well, let's choose what. Okay, so step 1, let's choose the instance first. So what do we want to choose as time 0? Yet released. And time final? Hits the ground, yep. Okay, so at time equals 0, the ball's right here at that star. So I'm going to put the origin on the ground right beneath that. And I'm going to put the y-axis up and the x-axis that way. So the origin location and the coordinate system orientation, those are just shown in the picture. And now we have to think about what variables we know and want. Do we know the elapsed time before it hits the ground? Nope. If we can get by without it, that's fine, though. Do we know anything about the initial position? Yeah, so we know that this was supposed to be part of the problem. The height is 1.5 meters. Okay, so when time is equal to 0, the ball's right here. So can we come up with either of the coordinates at that point? That's what that initial position is asking. Do we know the x coordinate of that point? What is it? 0. Yep, you don't have to go horizontally at all to get to that point. So Pix is 0. And do we know the y coordinate? Yep. 1.5. Do we know anything about the final position? That's right. Yep, very good. So we know that at time final, the ball is right about to hit the ground. So its height is 0. Since our, the origin is on the ground, the y position of the ground is 0. So Pfy is 0. Do we know anything about the velocity at time 0? We can get that from the speed and the angle. So these come from 40 times the cosine of 25 and 40 times the sine of 25. Can someone calculate that? I have different numbers in my notes. Okay. $16.92. And these are in meters per second. Is that right? Oh, 90. Okay, so the x component of the velocity at that instant is 36.25. The y component is 16.90. Do we know anything about the final velocity? We don't. I'll tell you something that you do always know, but we're always going to pretend like we don't know it. Like we're going to pretend like we learn it fresh every time. Since the acceleration is only in the vertical direction, gravity only acts up and, well, it only acts down. There's nothing, and since we're ignoring air resistance, there's nothing to change the x component of the velocity. And so the x component of the velocity final is always equal to the x component of the velocity initial. But we're going to pretend we don't know that, because otherwise it sort of messes you up, thinks you can use equations that you can't. And then the last thing is acceleration. Oh, I skipped something. So we know the y coordinate at time final is 0. We don't know the x coordinate, but that's what we want, right? We're trying to find horizontally how far away it lands. So this has to be Px. And then the last thing is we know the acceleration. Ax is 0. Ay is negative 9.81. Okay, so is there an equation that works for these? It's a pain now because you used to have 3 equations to look through to see if they work. Now you have 6. But if you did go through them one by one, you'd see that there isn't one that works. Well, at first you'd think there is, right? You'd think 2ax times quantity pfx minus pix is equal to vf. Oh, no, you know what? Let's ignore that. Pretend I never said anything. So actually, you would think that you could use that one if you use the fact, put the fact on here that pfx is the same as pix. It's true, but it'll screw you up, and it'll make you think you can use that equation, and then it'll end up not giving you anything. So if we don't put that down, it looks like there's no equation that works. And if no equation works, that means that we want to find time final. So is there an equation that works so that we can find time final? It would be pretty weird if there wasn't, you know, because I told you that's the only thing to do. Yep. The first one won't work because we don't know any final velocities, but the second one will work. The y component of the second one. So pfy is equal to piy plus viy tf plus 1/2 ay tf squared. So that says, oh, and by the way, now you can stop carrying units through your calculations. We're done with that. So 0 is equal to 1.5 plus VIY was 16.90. And then 1/2 times negative 9.81 is negative 4.905 TF squared. How can we solve that equation? Quadratic formula. Anybody have that in a program in your calculator? Can someone calculate this for me? So quadratic formula, this is A, this is B, and this is C. And it gives 2 roots for time final. 23.5? Oh, 3.5. Okay. Negative? There should be a negative one and a positive one. .337, and then what was the other one? 0.090. Anyone else get that? .353. Okay, and then negative 0.090. 86. Oh. Okay. What? Oh. Okay. So which one of those do we take and which one do we reject? It's easy when you're dealing with time. You just always take the positive one. So now we know time final. Now we can use that to solve for the variable we wanted in the first place, pfx. So what equation, now that we know time final, what equation will work to solve for pfx? And the answer, when you do this, it usually works this way. The one we want is just the x version of what we used for time final. So PFX is equal to PIX plus VIX T final plus 1/2 AX TF squared. So that's 0 plus 36.25 times 3.53 plus this whole thing is 0 because AX is 0. And so what's 36.25 times 3.53? $127.96 meters, which is 350 feet or something like that. Any questions about that? Okay, now the next thing I want to do is, this is something that's a common misconception about how two-dimensional motion works. Commonly misunderstood. It turns out that the motion that happens horizontally and the motion that happens vertically are totally independent of each other. What's happening in one direction doesn't have any effect on what's happening in the other direction. Okay, so here's what happens if you, okay, so here's one person, and here's another person, and this person has a gun. It's like a dirty, hairy gun. Okay, so this person shoots a bullet, and this person drops a bullet at the same time. Okay. Which bullet hits the ground first? The one that's shot or the one that's dropped? The intuition that I just feel like they should be enclosed. Okay, so the intuition that most people have sort of naturally is that there's something about the really fast horizontal motion of the bullet that's going to keep it from hitting the ground as quickly. The one that's dropped is going to hit the ground first. Okay, that's a pretty common intuition that people have. The truth is that what's happening, the fact that one of them is going horizontally really fast doesn't have any effect on what happens vertically. And so the bullet that's being shot, even though it has a really big horizontal velocity, it falls just the same as the other one in the vertical direction. And so those two are going to hit the ground at the same time. It's a little bit of a weird thought to a lot of people, but it's an important idea to recognize that what's happening horizontally and vertically are unrelated to each other. So I want to show a Mythbusters video of this, and then we'll do the calculation and see mathematically why it works. Okay, I think we'll probably do the calculation next time, but let's watch the video because everyone likes movie day. Okay, just a second. Okay.
Needed to match the solenoid.
Okay, so this is from Mythbusters.
And after a few test fires and a bit of fine-tuning, it works.
Oh, it's good. It's good. It's 1/3 of a millisecond difference.
Wow.
That's freaking perfect. Let's go do this full scale.
Okay.
Which means rolling up the room 360 feet to stake out a drop zone.
Right about there. That's where they were landing out in the shooting range, so this is where I expect them to land here.
Okay.
Adam lays down a runway of white paper so the high-speed camera will clearly see and measure both bullets at the same time, in the same place, and in the same shot. All we need now in the drop zone is Jamie's drop rig, so the boys can take a shot at physics history.
All right, dude, you ready to do this for real?
I think we'll hit it on the first shot.
Really?
Oh, yeah.
You never make predictions. That's awesome.
Bullet drop versus fired. In 3, 2, 1.
But from 360 feet away, the boys can't see exactly where the fired bullet landed.
Let's go see where it hit.
So Adam takes a one-wheeled ride down the room to check out the drop zone.
Wow.
And the results are simply ripping.
Can't get much closer than that. I can't wait to see the high speed. So, dude, this bullet carved a streak right under the drop zone. I think this might be the shot we've been looking for.
In real time, it's impossible to tell what happened until Adam analyzes the high speed and crunches the numbers.
3677 minus 3915 equals 238 divided by 6. Dude, the difference is 39.6 milliseconds.
Which means it's less than the human eye can make out.
So after days of brain-teasing tests, the Mythbusters can claim a world first for themselves and a victory for physics.
That's pretty interesting, isn't it? Even for the most cynical among you. See it again?
All right, Jamie. This one's from 200 yards.
Can you dodge a bullet?
Okay, fire
Don't do
well.
that.
All right.
Needed to match the
I'm guessing no.
Everything's hot. Let's do it. 3677 minus 3915 equals 238 divided by 6. Dude, the difference is 39.6 milliseconds.
Which means it's less than the human eye can make out.
So after days
I would
of
guess that
brain-teasing
the
tests,
error that they get is
our
just
Mythbusters
from the alignment of the gun. You know, like when it's going that fast, any little problem with the alignment makes a huge difference, I think. I'm going to do that calculation too when we do it. So what we'll see is if you fire a bullet horizontally and drop a bullet, they hit the ground at the exact same time. If you drop a bullet at the same time you fire a bullet 1 degree above horizontal, that's a tiny amount, right? 1 degree is a really little angle. This one hits the ground like half a minute after this one, something like that. It's incredible the amount of, and it just has to do with how fast it's going, you know. So like a tiny little error in aligning the gun would give you a noticeable problem. 15 quiz time. Did everybody get one? Hi. That's right. Hi. Oh yeah.
In your office, or can I go grab them?
Yeah, they're in my office, I assume. Yeah. You want to come with me after everyone's done here? All right. Yeah. Hi.
I wasn't supposed to know, so you wanted to trust that.
Yeah, I did. You want to come up with us after everybody's done here and get it? It's in my office. Hi.
I emailed you about scheduling an appointment for this hour.
Yeah. Oh, okay. What tomorrow? Do you have time?
I leave at like 11.
Okay.
But I have a break in between classes from 9 to 10.
From 9 to 10.
there. Otherwise, I could just like stay after 11, but I could only
Yeah.
stay till like 12.
What days work better? Any?
Yeah. I mean, like, when are
Thanks.
you? Because I have a lot of breaks.
Mondays?
Okay, I have break Mondays 9 to 10, and then 12 to 2.
Okay, how
So,
about
right
like,
before that?
yeah, how about right before lab?
Okay.
You know where my office is? Let's do it in lab.
Okay.
I think it's open.
Okay. Cool.
Okay, bye. Sure. Hi.
Staying on the problem you just did. So why is the x 0 and the y? Because
Okay,
So
because
so-
let me just draw it. Yes, Frogman. Okay, so all what we know is that the acceleration of gravity is straight down, right?
Yep.
And so if you put that on the
Oh,
coordinate system, then what you're doing is coming up with the coordinates of that point.
Sure.
And so that's 0x 9.81 down.
Right. So it'll never. So the acceleration of x will always be 0 then.
Yes, as long as your y-axis is up. You know, I mean, you could do a wacky coordinate system
Sure.
like this,
Right.
and then it wouldn't be, you know, because the thing it always does is
Right.
go down.
Right.
But as long as your y-axis is up, then
Up.
yes,
Okay.
it'll always be that.
Okay. Awesome. Thank you.
Sure.
Oh, thanks.
Bye.